Okay, so today, this is AM1 Lesson 6 for 8th grade. Now, 9th grade math, really. This is algebra. We are going to talk about distribution. We're going to prove distribution, and we're going to show this isn't just a simple distribution that you know how to do. We're going to get into a little bit more advanced distribution and understanding how we can apply these concepts to solving some algebraic questions that aren't obvious. And actually answer some questions from a couple months ago that we've asked about how you square various binomials and other kinds of questions. So keep your eyes open for that, and you'll see what I mean, that this is a little bit new for you. It also answers some questions about some problems that some of you on Alex were maybe having some difficulty with, and this will become old hat hopefully after this lesson. So let's move on to the lesson on distribution and understand just the basics of distribution. So let's start off over here. So we're going to prove, so this is distribution. So this is AM1 Lesson 6, and it's distribution. And this is a basic property of mathematics. It has to do with why is it true that 3 times 2 plus 5 is equal to 3 times 2 plus 3 times 5. So why is it always true that you can do this? So, you know, if I was to evaluate this side, I'd get, well, 3 times 7, and I'd get 21. And if I'd evaluate the other side, I'd say, well, my order of operations says to go 3 times 2 is 6 plus 15, and that equals 21. So this law of distribution is true, but why is it true? And the easiest way to see it is through geometry. So remember that all algebra can be shown as geometry, and all geometries basically can be equated to algebra. And that was, proven by Descartes long ago. And we don't, the proof of that, I don't even know how to do all of it, but certainly it is true. And here's an example where you can see it more proof more clearly with geometry than you can normally see it with algebra. So let's just look over here. So we're gonna make a line here, and we're going to go from this is the algebra world, and over here we have the geometry world. So let's look at a piece of at a rectangle, and in this rectangle we're going to say that there's a side that has a length, a width. We're going to call this the width, and we're going to call it a width of 3. So that's going to be this side here. And here's our rectangle, and we're going to divide our rectangle into 2 pieces. So we're going to say that this side has a length of, we're going to, from here to here has a 2, and over here to here has 5. So it's 5 from here to here, and it's 2 from here to here. So if you look at it from the top, you have a length of 5 plus 2. If you look at it from the bottom, the whole length is 7. Okay? Now the question is the area of this whole rectangle equal to the sum of the 2 parts? So if I take part A and I take part B, the whole rectangle's area should be the same as the area of part A plus the area of part B. And that just makes sense. The sum of the whole is the sum of its parts. So the whole is equal to part A plus part B. So if I think about this whole, I can think of it as 3 times 7, but let's think of it a different way for purposes of this proof. And let's say that this whole is the length, or the width, sorry, the width is 3, and the length is 2 plus 5. Because that's the definition of area. Now, part A, let's look at part A. What is the area of part A? 3, well, it's 3, the width times its length. And the area of part B is 3 times 5. And hence we've proved geometrically the property of distribution. So that's pretty cool. So we've gone into the geometry world to make a proof about a property that we know is true. Now, let me make a few more points about this before we go on. Distribution works across terms inside parentheses. So realize that we have 2 terms inside this parentheses, a 2 and a 5. And we know that these are 2 terms because they are separated by an addition sign. Right, there's our addition sign that divides our 2 terms inside the parentheses. Distribution does not work if this is a multiplication or division. It only works with addition because you can only draw this geometric proof by adding 2 pieces to a side. So let's be really careful about that. Or subtraction. It works for addition or subtraction, but not multiplication or division on the inside. Okay, now another thing is this distribution thing also works if you divide things like this. If you have 2, 3, and 4, and this side is also, let's say this side is 2 also. So it can be 2 times 2 plus 3 plus 4. It can work for any number of terms inside the parentheses. So this is equal to 2 times 2 plus 2 times 3 plus 2 times 4, which is equal to 4 plus 6 plus 8 equal to 18. Or we could have said it's 2 times 9 also equals 2 times 9 because 2 plus 3 plus 4 is 9. So it equals either one of these things, and 2 times 9 is 18. So again, the whole is equal to the sum of parts. And that proves distribution. So again, the key takeaway is the whole is the sum of the parts. So we use geometry to prove distribution by looking at the whole and the sum of the parts. Now, let's get on to something a little bit more interesting, perhaps. Well, let's just prove this more generally. So it's not just that you substitute in any numbers and you get, distribution being true. We can prove that it's true for any numbers. Any numbers x, y, and z that I can put into a rectangle, or into a rectangle like this, which is any numbers, is always going to be true. So because the area, the whole of this thing is going to be x times y plus z, the length times the width, is going to equal to part A. Part A is just xy. And part B is xz. All right, so xy plus xz. So it works. So distribution always works. And this is your general proof. Well, actually, the whole thing. The whole thing. Here's your picture, and here's your algebra. Okay. So let's take one step back, or one step forward, or let's think about this for a second, and let's ask the question. Knowing what we know now about how to prove distribution, I want you to think about a plus b squared and ask yourself, is that equal to a squared plus b squared? Now notice this symbol here. This symbol here does not say, does not say they are equal. It asks if they are equal. So that's this equals with a question mark over it. It's asking if they're equal. Now, it looks reasonable to say that, but it is absolutely not true. And there's two ways the answer is no. This is not no. And there's two ways to do it. One, you can just test with any numbers. You can disprove any conjecture by saying, well, let me plug in a number. Well, let's try this. Well, let's say if A is 1 and B equals 2. Let's see if this is true. So is 1 plus 2 squared equal to 1 squared plus 2 squared? Does 1 plus 2 is 3. Does 3 squared equal 1 squared plus 2 squared? Does 9, does that equal 1 plus 4? Does it equal 5? And the answer is no. So this is called a proof by contradiction. So I have this rule, and I just prove that it's not true just by finding one example of this not being true. If this is true, it's got to always be true. So you can know, for example, that like x times y plus z equals xy plus xz. You can try this with any three numbers, x, y, and z in the world, and this will always, always, always be true. So let's see then, what does a plus b squared really equal? What does it equal? And we're going to go right back to our tried and true strategy that we just used above and say, well, let's use multiplication. Let's use geometric multiplication to find out. So we're going to say, we're going to make make one rectangle with one side that's A and B and another side that's A and B. So what is the length of this, or the width of this rectangle? The width of this we're going to look for the whole area in equals the sum of parts. The whole area, and we're just going to do this on another page, just so we don't run out of space. There we go. So here we go. A, B, A, B. And so we're going to say the whole area equals the sum of the parts. Now notice, in this case, we have 4 parts. In our other examples of distribution, we either had 2 or 3 parts. Here we have 4 parts. But we know that we're going to look for the whole area equals the length times the width. The length is A plus B. And the width is A plus B. And we know that A plus B times A plus B is the same thing as A plus B squared. And that's what we were trying to find. This is what we were trying to find out. What does this equal? What does that equal? Well, we can find out one way by simply adding up the parts. Well, let's look at this square. Square number 1 right here. Well, this length times, or this width times this length, this is, well, that's a squared. This square is a squared. Well, this square here is a times b. So this is ab. Well, this square here is also ab, or this rectangle. And this is a square with a side of b and a side of b. So the sum of our parts, a plus b squared, it's got to be that plus that plus that plus that. It's got to be those 4 things added together. So if we rewrite it, a plus b squared must equal a squared plus ab plus ab plus b squared. Has to be. And that's another way of looking at that. We have to combine these 2 terms. These are like terms because they have the same variables, same exponents. So we have a squared. If I have one ab and another ab, well, that's 2ab plus b squared. And this makes more sense because remember, if we go back and we can just test it, let's just test it with one set of numbers. Testing it with one set of numbers doesn't prove anything, but let's just watch what happens. 1 plus 2 squared is 3 squared. And then we have 1 squared plus 2 times 1 times 2 plus b squared, which is 2 squared. So that's 1 plus 4 plus 4. Cool. So 9 equals 9. So it's looking like this is plausible, and in fact, it is true. You can't find any numbers that this is not true for. I challenge you to go out and find any 2 numbers, positive, negative, fractions, or anything where this is not true. Well, it's always, always, always true, and that's because we can draw it geometrically and prove our point. So let's end there. Well, let's just apply this in. Let's apply it one more time for one more example. If you want to be done, you can be done. If you want to try this example, let's just look at one more. Well, notice this does not equal x squared plus 4. And we can show that this way. This will be 4, this will be x, this will be x, and this will be 1. So x plus 1 times x plus 4 is going to equal, this box here is x squared. This box here is 4, is x on this side and 4 on this side. That's 4x. This box here is 1 on this side, x on that side. This is an x. And this box here is 1 on that side times 4. So this box is equal to x squared plus x plus 4x plus 4. And we can combine our middle 2 terms. And we can come up with x squared plus 5x. 1x and 4x is 5x plus 4. And we can try this with any numbers we want. If we wanted to plug in some numbers, let's just try plugging this in with x equals 2, and then let's try plugging it with x equals 0. So let's see. So x plus 1, if it's a 2, we'd have 2 plus 1 times 2 plus 4. And our question is that equal to 2 squared plus 5 times 2 plus 4? Does that equal? Remember, if we're trying it with x equals 2, we just take x and we plug it in for each 2, and we plug it in for each x up here. So is this true if x is 2? So 2 plus 1 times 2 plus 4, does that equal 2 squared plus 5 times 2 plus 4? Well, let's see. This is 3 times 8. Does that equal 4? Times 6, sorry, times 6. 2 plus 4 is 6. Sorry. Does that equal 4 plus 10 plus 4? Well, does 18 equal, well, 4 plus 4 is 8 plus 10. Does it equal 18? Yes. Well, let's try it with another number just to see if I'm crazy. So if x is 0, let's go ahead and plug a 0 in up here. Well, does 0 plus 1 times 0 plus 4, well, that equals 4. And does that equal x squared plus 5x plus 4? Well, does 0 squared plus 5 times 0 plus 4, well, that equals 0 plus 0 plus 4. Well, that also equals 4. So check. So that's the way that we can test. You'd have to prove it by testing numbers. You'd have to try every single number in the entire world. But the way that you can prove it is always true is you can always go back here and use your geometric proof, which says that it's always true that x plus 1 times x plus 4 must equal x squared plus 5x plus 4 because the whole must equal the sum of the parts. Okay, well, we will be done done now. We will sign off and we will say that our work here is done, and I love distribution too. Love it to death. All right, see you in class. Enjoy your break.